All right, and here's our third and final recording of acceleration due to gravity problems. This one is the type of problem that happens when you throw something up and it comes back down, which is just like our last problem, except you are not standing on the flat ground. So it's kind of like, let me see. What happens with this situation is that, generally speaking, there's a cliff or you're on a ledge and you throw something up into the air, and then that comes back down. So it's like this, and then it'll go here, and then it might even keep coming all the way back down to the bottom ground. Okay, so in this situation, a student stands on the edge of a 45-meter high cliff, and they throw their physics homework straight up at 12 meters per second. And how long does it take to come back down to the same height as the student? High voices are my children. Sorry, guys. Okay, so in this case, they only want to know how long does it take to come back down to this height right here. So they want to know the time up and the time down. Okay. Now, you could go ahead and do this just the way we did the other problem with the initial and the final velocity. That is definitely one way to do this. Actually, that is the way we're going to do this. Okay, start with your variables. You know you have a final velocity, you have an initial velocity, you've got an acceleration, a displacement, and a time. Those are all of your options. If something is thrown straight up in the air, our initial velocity, according to the story, is 12 meters per second. And if it's thrown straight up into the air, the instant that it's thrown, right after that, there's nothing acting on it except the acceleration due to gravity. So our initial velocity is that. If something is thrown, keyword in there, that tells us that we are talking about an acceleration that is negative 10 meters per second squared. They want to know how long does it take to come back in. And the other number that's in here is that 45 meters. Okay, that 45 meters, I'm going to put it on here because that tells us something. But it does not tell us anything about that part of the problem, because that's all below. That 45 meters is all below it. Okay, so unfortunately that 45 meters will not help us at this particular moment. But we do know from our last problem that your initial velocity, right, because of symmetry, what goes up at 12 meters per second, at that same height on the other side will be negative 12 meters per second. So our final velocity, if you talk about the same height, if we throw something up and it comes down to the same height, our final is equal to our negative of our initial velocity. That's negative 12 meters per second. So again, we're not going to use the delta y on this one because it just does not pertain, leaving us the equation final velocity is equal to initial velocity plus acceleration times time. We're going to rearrange for time. Subtract your initial velocity from both sides. Final velocity minus initial velocity is equal to acceleration times time. Divide both sides by acceleration. You are left with final minus initial velocities divided by acceleration is equal to your times. Okay, so it's negative 12 is our final, minus our initial velocity of a positive 12, divided by negative 10. So that's negative 24 divided by negative 10. The negatives cancel out, and we're left with, it takes 2.4 seconds for the object to both come up and come straight down. From here, you could also know that if this is your up and down, that if your time up, if you want to do just the time up and just the time down, that would be 1.2 seconds up, and because of symmetry, it would be 1.2 seconds down. Okay, now the next problem. So if you throw it up and it falls all the way to the bottom of the cliff, how fast is it traveling when it hits the ground? Start with your variable list again. Final, initial, acceleration, change in position, and time. Okay, so our initial velocity is going to be a positive 12 meters per second because it is being thrown up. This time we are not going to use that negative 12 because we're not going for that. We're not doing that anymore. We are now going for how fast is it going here. Okay. I know that it's a bit tempting to say, well, when it hits the ground, it's going 0 meters per second. All right. We're not looking at it exactly. When it goes 0, that is right after it hits the ground. So it might even be better to say that at the instant just before it hits the ground, how fast is it going? So we're looking at the instant before it becomes 0. Okay, before a force changes it. We're looking for how fast is it going before a force changes the motion. So when you read that, how fast is it traveling when it hits the ground, they're not looking for that 0 because it's hit something. They're looking for in that bare instant before it hits something, before something changes its motion, how fast is it going? So in this case, it's not 0, it's a question mark. It's what we're looking for. We don't know how fast it's going. We do know that it was thrown, which gives us a acceleration of negative 10 meters per second squared. We do not have the time on this, but we are going to use that delta y. That is going to be 45 meters, and it's going to be negative. Okay? Because we're looking for our change in position. If the cliff is our initial position, okay, and we are now going to our final position, which is 45 meters below our initial. That's how that one comes out. So there's no time. And we are looking at what equation does not have time. That is our final velocity is minus our initial velocity squared. Is equal to double our acceleration and our vertical displacement. I'm going to move that initial velocity over by adding it to both sides. That cancels. And we're left with final velocity squared is equal to 2a times acceleration times our delta y plus initial velocity squared. What I do now is I'm going to square root it because I do not want final velocity squared. I just want the final velocity. So final velocity is equal to double my acceleration and my vertical displacement plus the value that is my initial velocity squared. So I'm going to come back in and put all our values here. And we are left, so our final velocity is equal to 2 times negative 10 times negative 45 plus 12 squared. Then it's just calculator time. And that will give us 32 meters per second. While you think about this, is this going to be a positive or a negative velocity? All right. When you do a square root will always give you a positive or a negative answer. It is up to you to choose what it's going to be. In this case, I'm going to choose negative 32 meters per second because it is going, the direction at that instant is down. And that is your third example problem. All right, that should take care of your notes. Feel free to post any questions about these notes on Edmodo.